We'll start in few minutes. Hello everyone. I'll share my screen. Uh, is my voice audible? Is someone text in the chat window? Okay, week 6. Okay. And okay, so we'll be starting content of week 6. Let me see first what is there in the week 6. Any doubts, any questions from the assignment? If you want to clarify, you can start asking. Uh, so- yes, till week 4 we have completed everything, and we will go to week 5 now. And I will briefly uh, I'll briefly discuss about week 5 and week 6 materials today, and then we'll go to some code examples that is there. Okay, and yeah. So let me close this one. Okay, so let's just start with our discussion of so in week 5 we saw that the like if you have say if you have gone through week 5 contents, here we have cost function, classification cost functions, optimization technique and learning rules, and gradient descent learning rules, AZD and Adam learning rules. So these are basically basics of deep learning. I have covered it in week 2 or something, but I will try to go deeper this time. Okay. So I'll start with cost function. Cost functions. So in a neural network, so the basic operation is that the first step is forward pass. Second step is calculating loss. Third step is backward pass. Open. Backward pass, and fourth is update. And you have to repeat all these things for training any neural network. This I have discussed earlier. So suppose this is a neural network. Why is this happening? I don't know. Suppose this is a neural network and we're passing input I and we're getting some value y hat and there is a actual y. So let's say this is x and we're calculating loss y hat loss and we're getting something and then we're back propagating it to update all the weights. Okay. So so how so what is basically loss function? Loss function is something. So so we're now we'll focus on this part. Okay. Calculating loss. So I would say loss equals to cost. Same thing. We represent it as L or J. Okay. So what is a loss in a neural network? So what you can say is a loss in a neural network? I would say that you put that thing into the loss which you need to minimize or which you need to maximize. Sorry, minimize or which you need to optimize. So why do we need to optimize or minimize the loss? We need to minimize the loss because if we minimize the loss, uh, it will give us better weights and better optimized weights. For example, like if you see, so if you're suppose classifying cats and dogs, and if the input image is a cat, and you passed it to the neural network, and at the end there are two neurons, let's say. One is for cat, one is for dog. Okay. But at the end you got you know about sigmoid. We apply sigmoid before passing this to the neural network. And it what sigmoid will do is that it will squash the value between 0 and 1. Okay. Since it is squashing the value between 0 and 1, we'll get a probability score here and here, and this will add up to 1. Okay. Let's say you got a probability of 0.4 for cat and 0.6 for dog. For an image which is cat, this probability score is not a very good probability score because we want the probability score to be higher. Yeah. Am I there? I guess my internet connection got unstable for a while, but yeah. So I guess I am back online. So I don't want this my probability score to be lower for cat, right? I want it to be higher. So when I will punish, when I will calculate the loss, I want I want such weights in the neural network here. I want such weights in the neural network here, such that this weight will give me higher number of this cat probability. So for that we need better weights and better optimization, and for that we need to optimize in that way. So I just went off track some for a bit. So I'll just reiterate the thing that I said. Initially, there will be random weights, and I am passing the input to the neural network, and it is giving me a random score of 0.4 and 0.6. I need to punish or I need to put a loss in such a way that which should be minimized, and after minimizing that loss, I will be able to get that W, not some random W, but that optimized W, which will give me very correct version of correct probability score at the end. Like at the end, it will be something like 0.7, it will be like 0.3. The probability of this cat should increase, right? So so this loss function. So what we can do is that for this, let's say we got a score of 0.4 and 0.6. Okay, but what is our desired score? We need a desired score of 1 and 0, right? Because it is a cat, the probability should be 1, and it is a dog, it is not a dog, so the probability should be 0. And since we are looking into this, what we can do is that, so this is called a one-hot representation. So I'll talk a bit about one-hot representation because I think you need introduction. One hot vector. So suppose there is a categorical feature. So categorical feature means there must be a certain category. Like let's say the category can be weeks, or let's say numbers. So number of class, there's a 2. We're classifying cats and dogs. So we can say there are the labels can be either of 2. It can be cat or can be dog. The label is 2. If we are classifying 3 things, cat, dog, and bird, so there will be 3 labels. So we can assign, since neural network works in number fashion, we cannot just pass words. We have to assign a number. Cat 0, dog 1, bird as 2. Okay. So since this is the case, representing it into a one-hot vector will look like this. For 0, it will be sorry, it will be 1, 0, 0. For 1, it will be 0, 1, 0. For 2, it will be 0, 0, 1. Basically, we are taking a number and putting 1 in that place. So this is called one-hot vector. Okay. So first we need to represent the same thing as a one-hot vector. Since we got 0.4 and 0.6, so here the number is 1 and the number is 0. Okay. And one naive way is that we can take a difference, right? We can take 1 minus 0.4 plus 0 minus 0.6. So this can be our loss, right? Or the way we can define is that y1 minus y1 hat plus y2 minus y2 hat. But this will not give us a good result because we are just like trying to reach here to we're just trying to reach to 1, and we're like certainly not concerning about increasing the probability of these vectors. So that's why the loss that we use for classification is cross entropy loss. Let me see once. Okay. Is yeah, so it's called cross entropy loss. Cross entropy loss, and the cross entropy loss is something like minus y log y hat. Let me see this. Let me see. Uh, Cross entropy loss. Let me see the exact formula. I kind of forgot that. Okay, P log P. But which one is which? Yes. So this is the final formula, but the exact formula is loss cross entropy equals to minus I equals to 1 to k, where k is the number of classes. Let me see. K is the number of classes, and then yi log yi cap. Okay. So let's say here the k number of k is 2, because we are just classifying cats and dogs. So let's just rewrite this uh, loss function with respect to our requirement, and that will be summation of I equals to 1 to 2 and yi log y hat I, right? And let's say let's just put the values, and y1 is 1 into log y hat I is 0.4. I'm sorry. So this is yn y1 hat, this is y2 hat, and this is y1, this is y2. So y1 hat is 0.4, 0.4, uh, this is minus, this is minus 0 into log 0.6, and this part will be cancelled to 0, the rest will be minus 1 into log 0.4. So if you see, even if we don't have 2 classes, we have, let's say, 10 classes. In all the 10 classes, in one case, this number will be 1, others will be 0, right? So we can directly ignore all these things and say that, and one case it will be 1. In one case it will be 1. We can directly say that a loss, we can directly say that uh, loss CE equals to y log y cap. Let's say k, not k. Let's say rth class is our thing. So it will be minus yr log yr hat. Let's say the correct level is the rth. So there are like k classes 1 to k, and out of that number, rth class is the correct class. So in that fashion, the loss function, loss cross entropy will be minus yr log r. And since this is 1 for the correct class, the cross entropy loss is minus log yr hat. I guess you got the idea. Idea about cross entropy loss. And with this, we completed till this point cost function and classification cost function. If is there any doubt, you can ask now, or I can move forward with the lecture. Is this clear? I guess there is one participant, Sumit. The timing is such a way that not all people are joining, so it's fine. I'll just discuss everything and put it in the internet. If someone wants to refer to that, they can definitely go and refer. Okay, I got a yes, sir. It's fine. Then we'll go to the optimization technique and learning rules. Let me see what is there in this. Let me see what is the content in this. Then I can uh, correctly say what I'm trying to. So there are some other loss functions that are discussed in these slides. I'll go through that once.
And on the previous state of my weight, my net worth into next.
I'll try to download this and put it in there. Hmm. So this we talked about classification cost functions, but let's say we will start about the types of cost function that is there in this deep learning context. So the first one will be classification type, where we are dealing with classification task, and second will be regression type, when we are dealing with regression tasks. So in classification, there are basically four types of cost function. One is binary cross entropy or normal cross entropy that I discussed now, negative log likelihood, margin loss, and soft margin loss. I will discuss the first two, and the last two are not generally used, but yes, it will be used once you go in the advanced concepts of deep learning. Uh, the binary cross entropy, if you look into the formula that I discussed, it's minus y log y hat and summation of I equals to 1 to k yi log yi hat. Okay. If you look into that, you can see that. So this is very similar, very much similar. And this is just another way of representing the same thing. And let's just forget about this weight factor for now, because it's an additional step. Okay. So here k equals to 1 to k, here I equals to 1 to k, and k is the number of classes, total number of classes. And tk is the binary level of target class, which is like yi. log OK, which is log yi hat, which is our output. And if I expand this, I will have so since uh, this will have our target will be 1 here. So it is in this way that it is in this way that if 1 will be 1, second one will always be 0. So you can see that we just have one term, and here they have two terms. Along with this, they have another term here. But the target can only be 0 and 1. See, it is a set of 0 and 1. If this is 0, then this term will be 0. And if it is 1, this term will be 0. So at a time, only one term will be there. So to summarize, if tk is 1, we have yi log yi hat, like tk log OK. And since tk is 1, 1 minus tk will be 0. And this entire term will be 0. So the left the thing that left here is that this part, which is nothing but summation of small k equals to 1 to large k tk log OK. And I can just map these things. Small k equals to I, tk equals to yi, OK equals to yi hat. And after mapping, you can see that this formula is exactly similar to that I discussed earlier. So binary cross entropy is same thing. There is nothing difficult in binary cross entropy. Then we can come to negative log likelihood. It's a straightforward loss function, which says that just take the average of k equals like from k equals 1 to k. What you can do is that you have to assign certain weight to certain class, and you just have to multiply with uh, the target that you're getting. So here you can see that we're not using any target y. We're just using we're just using the we're just using the output that we're getting as yk hat. And this is the yk hat is similar to yk here, but since I uh, named it as yk hat for the output, and yk has the actual label, I am putting that as this. And here what we're doing is that we're minimizing the log likelihood of the our output. And when we're minimizing the log likelihood, it will minimize the likelihood of an event or of an label to appear for a target y. So this is the case. So this is a normal loss function. Nothing to worry about this. It's just a variation of that. Here we had log there, but here we don't have log. That's it. Margin loss, and uh, soft margin loss is something that we can discuss later, because these are not that important for classification point of view. All the things that will trend today will be of NLL or log likelihood. Sorry, LLL or binary cross entropy loss. Similarly, regression cost functions. So if you could remember, in regression, we so here in classification, we're getting a probability distribution. Like we'll get the output will get P1, P2 up to Pk. And here all the probability values, and if I sum Pi, I'll get 1, because summation of all probability value should add up to 1, right? But in regression, this is not the case. In regression, we will get output as real numbers. Okay, R1. Let's say. Okay. And since we're getting a real number as output, we need some other treatments. So the first one is L1 loss. You know, the L1 loss is just mod. So what you have to do? So you have a so let's just talk in this notation, because it's a different task. So let's say your neural network is outputting something, say O, and you have a target, say T. So for L1 loss, what you need to do is that just take a difference, target output minus target, take a mod. So since we have this mod, you can also take T minus O. Okay. And that's it. And since so if you're working with multiple neurons, you can just put a K here, and you have to summation. So sum all these things and take the average. Okay. So this is just a difference. You can say there's the difference with modular difference, and this is like, and we're just taking a bunch of it and taking average. So we just straightforward. And the second one is MSE loss, or the mean square error loss. It is same as the L1 loss, but instead one difference is that it is squared loss. So you will get a square loss. That's it, nothing else. But yeah, the third one is the KL divergence. So this is the important one. You have to take, you have to like keep be attentive here. The KL divergence, KLD, can say KLD. Suppose here is a number y. Sorry, let's say number n1. And there is number n2. How do you compare these two numbers? Like, how do you say that these two numbers are closer to each other or away from each other? You can just take a difference and take a mod. If it is smaller, then it is closer. If it is larger, it is far away. Okay, right? But the thing is that how do you do the same thing for a probability distribution? So suppose, let's say there is a distribution P1 and there is a distribution P2. So how do you define that these two probability distribution are similar or dissimilar? So for that we need divergence. How diverge these two distribution are, and one way to measure this divergence is the KL divergence. And since we're looking into KL divergence, I can say that since we're looking into KL divergence, I can say that I can say that this is the formula for KL divergence. And give me 1 second. The formula for KL divergence, and the formula is, it is similar, like minus 1 by K, Tk here is Yk, and log Tk by Ok. Ok is Y hat K. So this is the KL divergence between two probability distribution. Here the probability distribution is itself the label. So you can directly put Y and Y hat here, and you'll get a difference between these two distributions. Suppose in the regression task, you have, instead of just one number, you just have, let's say, 4 number or 5 number, 10 number. So this will represent a distribution, right? So what you are doing is that you are comparing this to the actual distribution. Since this is not a classification task, all these numbers will have some value, and together they can represent as a distribution, and by comparing these two, so to compare these two distribution, you have to put the KL divergence loss. This conclude the loss function that we have right now. I can go further. Yeah, I can go further now. And next is the optimization technique and learning rule and graded lesson learning rule, SGT and ADAM. So I'll go to the learning rules, but before that, let me see if there any notebook associated with this uh, part of the lecture. Lecture 20 is, this is lecture 21. Lecture 20 was denoising autoencoder. Okay. Lecture 22, cost functions. Okay. We can run this notebook now. Like then 24a gradient descent learning rule. Yeah, we can run, this is gradient descent learning rule for every training example. 25 is SGT and ADAM learning rule. 28 is, let me say, yeah, LeanIt. So 28 is different. We'll go till 22, so 25, 4C, and we'll start with 22. Okay, cost functions. So I'll run this code and I will talk about how to, because these are just formulas that I said. You can directly code it or you can use it from a existing package. So I would suggest that you should always use a existing package because these are very much handy and you can really take advantage of all these things. Okay. Yeah, I need to install this thing. Give me 1 second. Uh, nice spider. Yeah, we got it. Okay, let's just start running. So initial is we are just importing all these packages and compare SSM from SK image.measure. We're getting an error from the notebook that is there in the GitHub. Let's just try to debug this. Is removed. Structural similarity. This is working. Then we'll load the data sets now. It is loaded. Then we'll check the GPU. GPU is available. Then we'll define the autoencoder. So autoencoder that we discussed last class. So we have like 784 dimensional input, 400 dimensional Latin vector. Then again, from the 400 dimensional Latin vector, we're recreating the 784 dimensional image. So we're taking two instances of the same network and we're training it. Okay. And where did we define the criteria? Let me see. Criteria is, let's see. Okay, so we're passing the criteria, and so let's see the training mode. We have to put the network in the training mode first, because in the training mode we want the weights to change, but in the testing mode we want the weights to stay still, do not change. So that's why if we put net train, just call this function, it will put our network into training mode. By default it is in training mode. I don't know why they put it here. And when you do net.eval in the bracket, and then again this curly braces, not curly, like this round braces, you will get into the evaluation mode. And in the evaluation mode you can evaluate all these things. I mean, in the evaluation mode you can uh, use it for other test time. So then we're doing the optimization. Optimizer took 0 grad, and this is the forward pass model data input and getting the output, and this is the loss, the second step. The criterion is the, we can say, criterion, loss and cost is the same thing. Okay. And this is the loss criterion, and we're passing output and label, and we're getting the loss. This is the backward propagation, loss dot backward. This is the optimizer step, optimizer dot step, like is the update rule. Then we're returning the loss dot item. So this is the function for training, and this is the actual training code. And for the optimizer, we're using Adam. So Adam is the latest optimizer and it's the best optimizer for optimizing neural network. And we'll be using Adam and SGD most probably every time. And this is the criterion. Okay. The criterion is the criteria for the loss. And in one case, so we're basically we made two nets out of the same network, and we're basically testing which criterion is the best. Optimizer is same for both the nets, and the criterion is different for both the nets. Like the criterion one is nn.msc loss, criterion two is nn.l1 loss. Okay. And these are some of the list for plotting. Okay. And SSIM is actually structural similarity metric, which gives how two images are structurally same. Okay. And then we are loading the data set, test images, test inputs. Okay. And then we are flattening the image for the input. Then our epoch starts here. Uh, yeah. Then my epoch start here. And in each epoch, what we are doing is that we are iterating through the train data loader. We are getting input and label for the data. We are then getting a view out of it, like we're just flattening the input. Uh, then we're taking the input and passing it to train function, which will do all the four steps. Then we're keeping track of the loss. Then we're appending all this loss for plotting purposes later. And these are all um, um, evaluation steps, and looking into how SSIM or the structural similarity between input and output, because this is the auto encoder. We want the input and output to be exactly same. And this is for tracking the loss. And this is just for plotting. Okay. Let me run this and start training. It might take time. Net is not defined. Okay, okay. 2, 3, 1, 2, 3, 4, 5. Here 1, 2, 3, 4, 5. Net optimizer criterion inputs. inputs. This should be net, and there should be labels, I guess. Let me see. Okay, it is starting to trend. How many epochs is there? 10 epochs. You can see that with MAC loss, the structural similarity is larger. Like it is getting better increasing with time. But with L1 loss, the structural similarity is increasing very slowly. And starting with the loss, L1 loss is starting very high and then it is decreasing, but mean square error is starting from a lower value and it is decreasing better as compared to the L1 loss. And the structural similarity, initially L1 was better than MSc, but eventually the MSc overtook the L1 and it is better now than the L1 loss. So hence we will use L1 loss, sorry, MSc loss most often while running any notebook. Okay. While running a autoencoder task. Okay. And we need to do the same thing for classification loss. This is for regression loss, regression losses, and this is for classification loss. As you know, for classification, we need a network. So this is a network, and the input is 794 because it is a MNIST image, and the hidden layer is 400, and second hidden layer is 256, and the third is 10. So why we are taking 10? Because the number of classes that we have is 10. So we need 10 output neurons corresponding to 10 classes. Okay. And this is a forward. So forward pass, how the forward pass should propagate. So it is defined here. I'll pass the input to layer 1, I'll get the output, and that output will be passed to layer 2. This is the layer 1 till the output layer. This is layer 2, and I will be returning X. Okay. And we're taking 3 instances of the same net, and we will evaluate it using cross entropy loss, NLL loss, and multi-margin loss. Multi-margin loss I haven't discussed yet, but you can run it. And this is the criteria for training the classifier. Like this is the 10 function for training the classifier. Here you go. And the rest of this are same, like forward pass, backward pass, code for plotting, all these things. Let me delete this and just train it for, let's say, 50 epochs. Hopefully there will be no error. Okay. So we can start we can see that the training has started. We'll wait till the training has done. You can see the accuracy and all, everything is like increasing uniformly. There is no such drastic improvement in any of the cases now. Let's wait for the end. Multi-margin loss is leading now.
I don't know what happened, but it is not showing anything now. Okay, it is increasing slowly, but it is not visible. Yeah, it is visible now. The 12th epoch, we have 97% in all the three methods. Let's wait for the training to end. It will end in 2-3 minutes or 5 minutes. The training has finally finished, and you can see that like let me go to the plot that is there. So all of them achieved around same accuracy. Yeah, you can see that the cross entropy and negative log likelihood law started very high, like 0.7. The multi-version law started low, and but everything like came to the same thing. And in case of accuracy, everything is like achieving same thing most of the time. So there is not much of a loss for this simple data set, but but there will always be difference when you go to complex data sets. So let's just take a 5 or 10 minutes short break. Then I can come back and start with the optimization functions. Hello. Took a little bit of longer break. Sorry for that. Yeah, so we'll start with the loss function. So we're done with the loss function. Now we'll start with this optimization technique and learning rules. Okay. Optimization. So as you know, optimization is something like we are optimizing something like let's say there is uh, let's say there is a function f of x. We want to either minimize it or maximize it. And let's just assume the function is convex. Okay. So this will be the minimum point, right? This will be the minimum point. And so let's say this is x, or let's say it is w. Okay. So in that way it will be w. And we want to find that w, which will give us lower limit of fw, or in this case fw. So this is the basic optimization thing. So here in this case we have loss function, and loss function is a function of w, and we want to find the minimum loss, or we can say I want to find the w such that the loss is minimum, right? So I have already discussed about the gradient descent rule, where there will be initial value w, we'll take the gradient at this direction, and we'll take the sign of it, and we'll move in the opposite direction of the gradient, and we'll take a smaller steps here, then we'll move here, then we'll move here. So we'll eventually we'll come to this point. If somehow we overstep this minima, when we come here the gradient of descent, the sign of gradient will be in this direction, we'll move in the opposite direction, and we'll come here. So this we have to do for the entire batch of the data set. Suppose there are 1,000 element data set, we have to do this gradient descent by taking a mean over 1,000 dimension. Okay. But if but if the image size will be larger, and image size will be larger, and if the entire data set is, let's say, 1 lakh or 10 lakh, it is very much not feasible to take the entire data set and take gradient of it and take one step, and it will be also computationally inefficient. Also, you can say that like we're looking into 1 lakh image and taking just one little step, so which is not very cost effective, right? Instead of doing 1 lakh, looking at 1 lakh images, what we can do is that we can just look at 10,000 images, 10,000 images, and take one step, then next 10,000, another step, then next one 10,000, another step. The step what I meant is that this one, this step, these steps, the descending steps. So this is called batch gradient descent, or we can say stochastic gradient descent. Okay, in the stochastic gradient descent, instead of iterating over the 10 lakh examples, we're taking we're like making it small chunks of 1,000, 10,000, or anything that you can decide, and we're taking a gradient step according to this, then into this, and according to this. Okay, but the catch here is that
Yeah, but the catch here is that so how efficient is this? So what will happen if I take gradient step with respect to small batches? First, the number of examples that I'm looking before taking a step will be less. Hence, I can make very good progression with time. Second thing is that if I look into the efficiency of it, it will be also computational efficient because we're just taking gradient of 10,000 sample, not 10 lakh samples. So this is the basic idea of it. And and one question you might ask is that instead of looking 10 lakh data set and we're looking into 10,000 data sets, is this kind of examples? My screen recording stopped. I don't know why. Is my screen visible now? Please, someone let me know. Is my screen visible now or not? Sumit, is my screen visible now? Because I got disconnected for a while. Screen content are visible. Okay. So so this is the batch size. And okay, so you're saying that earlier we're looking at 10 lakh examples, and okay, and we're deciding that okay, these are the examples and I have to take a step accordingly. And now we're like looking at just 10,000 examples. So is this a bad thing? The answer is no, because we could have, like, instead of 10 lakh, we could have 10 million examples. And in that way, we can say that 10 lakh is just a subset of 10 million examples. Similarly, we can say that, let's say there are like billions of cats and dog images, and we just made a batch size of 10,000 instead of doing it 10 lakh. And that explains that even if we're looking into 10,000 images, it will, the results will be, the gradient step that we'll be taking will be similar to if we look into 10 lakh examples at a time and take one step. And if we like reduce it very further, like you can just look into one example and take a gradient step, and that is called something, but this won't be efficient because we're just looking into one images and taking one distance, and the update here will be very zigzag, like, because we're very uncertain about like looking one thing and taking a distance. But here the update will be smooth, and you can get a, so the more you increase the number of examples, you'll get a smoother update in the gradient curve. This is all about like gradient descent, and this is all about like stochastic gradient descent. And so there are a lot of optimization functions that have been proposed, but in the course there is just two, SGD and Adam. Yeah, SGD and Adam. And since so Adam is the latest one, so you just have to use Adam. So I will not go into the formulation of Adam, but you can say that Adam is a variation of SGD, where we're also considering about momentum and what are the previous steps and all these things, and taking a step depending on all these things, not just examples. Okay. So I guess the time is running. So I guess I'll directly go to the notebooks now, and I'll try to run all these things one by one. There is 24A and 24C. I'll try to run this. These are small notebooks. So initially loading the packages as always, and loading the data and checking the availability of GPU. Then we're defining the neural network. The neural network is the same as last, like 28, 28, 400, 2400, 256, and the end layer is 10. Yeah, so we are just taking one neural net now and we're just passing it to the device. So this net.to device is transferring your neural network from CPU or your local device to GPU. If you have a GPU, you can have to do that. The device is defined here. Device is either CUDA or CPU. CUDA is stand for GPUs. We did that, and now we'll train the neural network with the optimizer as, let me see. Yes, so this is the gradient descent learning rule. So as I said earlier, let's say there are 10 lakh samples, but in MNIST, actually we have 60,000 samples, and out of which 50,000 is for training, 5,000 is for testing, 5,000 is for validation. Validation is that whenever training, you just need to check how it is performing on the next 5, because you are training in this 50,000 samples. If you give this 50,000 samples to the network, it will memorize that, okay, this is corresponding to this is corresponding to this, then it will give the results. But if you are giving a new some 5,000 examples, it will be confused, and the network will try to optimize over new examples. That's why we need the validation set. And after all the training is done, we will use a testing set to test the trained model. So initially what we're doing is that this gradient step, we're just doing the forward pass for all 50,000 examples. It will be forward passed. Then we'll calculate the loss, and all the 50,000. So the loss and everything will be back propagated for all the 50,000 examples, and we'll update the weight once. So we're updating the weight once after seeing all the 50,000 examples. So this notebook is about that. We're updating after looking entire thing. So this is a training code. Like iteration is 10, criterion is cross entropy loss as always, and this is we're setting it to train. Then we're iterating to the train pointer. We're getting the input and the labels. We're reshaping the input to 784 dimension. This is the forward pass. Second step, calculate loss. Then if I equals to 0, then we're taking a loss, and so we're just we're just accumulating the loss for entire thing now. And then what we're doing is that after entire data set is done, so see, let's say this for loop is till here. Okay, so what we're doing is that we're just accumulating loss here till the entire data set is done. Then we're taking a mean of the total loss, and we're doing the backward pass. Okay, this is the total loss, and this is the, and we're calculating the entire loss. Then we're doing the backward pass, and then we are updating the network, and we're appending the loss. And these are for validation step. These are plotting. Okay, let's just see how it is coming. Well, as I said, if you increase the number of examples per update, the update will be smoother, because it will see everything and then take a step. It is very confident about it. Its step. If you just look into some examples and take a step, it won't be that confident, and it will be zigzagging. Like it will go there. The next set of example will say, okay, no, that direction is not that that direction is not good for decreasing the loss. Let's just take in this direction. So in this way, like you'll get. So I'm hoping that this will be smoother. Yeah, see, the training loss is decreasing like very flat from 2.4 or something to 2.2, and and also testing accuracy is increasing very flat. Okay, and let's just go to 24C and see what is this. So here what we are doing is that we are doing this one, like we're looking into one example and updating the step. So here you can see, so everything else will be same, but I guess this will be different. See here we were till this point, we're not doing backward pass after one iteration, but see till this point, till the loss is there, and we're just taking the total, and all these things are outside because we're just iterating through the entire train loader and taking a step. But in lecture 24 C notebook, we can see that the input is first converted to the is flattened, then the output is so then we're taking the output and we're calculating the loss, and as we get the loss, we are just back propagating the loss, like for each training example we are taking a step. So that like the update step is after each example. Okay, so let's just run this and see how it is going on. Now training example is 60,000. GPU is available. Neural network is defined. Then we'll training the model. This might take some time, I guess. And now epoch 1 is over. Like it is taking step for each and every example. I guess that is why it is taking time. We have only 3 iterations to complete. I guess it will complete within 2-3 minutes. We're not getting any improvement over the epochs. Okay, we got it. And yeah, so you can see that the training takes a lot of time for looking into each and every example and taking just one step. And you can see the decrease in cross entropy loss is not that smooth. If you run it for like 10-15 epochs, you can see that it will be zigzag. It is not, the zigzag is not visible clearly here, but
it will be zigzag. Similarly, accuracy will also be zigzag as compared to this smooth increase in accuracy and loss. And the testing accuracy, yeah, the testing accuracy is better here, 97.5%, but here it is just 37%. And I guess like if I train it for more epochs, it will increase. Let me just train it for more epochs and see if it is increasing or not, since it should be increasing. Yeah, it is increasing, 41. The updates are faster here. So 47, 50, 52, 54, 56, 57. 59, we got till 59. Let's just 60. Let's just try to increase a bit more. Since it is taking very less time, I guess it's okay to do these things. 62. I guess the increase now will slow down for a bit. Yeah, 68. Got till 68%. So this is not bad. Like you can keep on training it and you get better and better score till 97. The point is that the increase in accuracy will be low here, but it will be faster as compared to taking a step, looking into everything and taking it just one step. So that was the point. And I guess we completed all the notebooks of week 5 till week 5 or something. Let me see. Till week 5 we have completed everything. Week 6 is all about CNN and stuff. We'll discuss that next class. Week 7 is variation of CNN. Week 8 is also variation of CNN. We can cover all these things just in just 1 week. Next week, CNN and its variation. It will be the next lecture. And also, like if you have been watching these videos, you can ask about covering the assignment questions, but we are instructed that we shouldn't be solving assignment question of this year in the live class. But if the answers are released and you are confused about that answers, you can surely join the live lecture and ask there, okay, this week's this question is my doubt, and please clarify that. And I guess we're near the end. We just have 5 minutes left, and in that 5 minutes, let me see like if I have uploaded all the videos till now. Similarly, I'll put this one. I guess okay, till week 5, I have uploaded all the videos. This is the week 6 video, and I will be uploading that. And there was a sit here in the sheet also. Till week 5, everything is there. From week 6 video will be live today. Yeah. So I guess this is the end of this today's session. Next session, I will try to cover most of the assignment questions. Yeah, thank you. You can leave Sumit now. Yes. Thank you.